Hi everybody, Mrs. Dinkelman here, and this is Unit 8. We're talking about improper integrals. Just a few pictures here of what an improper integral is. So really it's something that potentially could have, it might have infinite area, it might not, but the limits somewhere are infinite. So we need to figure out whether that area is going to be finite or infinite, which maybe seems a little strange because if we have something that's going along forever, remember we're talking about a limit. So what is our area heading towards as our bounds get further and further out? So that first picture really there would be like an integral from a to infinity. The second one, if we have an asymptote, that's what that's trying to show, is that at b perhaps there's an asymptote and what happens with that area as we go up, or something like the third one where in the middle somewhere there's an asymptote and what happens with that area. We're introducing some new vocab, and that's whether something converges or diverges. So when we find our limit, our integral, and we find a finite number, we can say that that integral converges, or the area under the curve converges. That's a finite number. If it's divergent, what happens is we either get infinity as our answer, or basically something doesn't exist. The example I can think about something not existing is the limit as x approaches infinity of a sine or a cosine, where we have something that keeps oscillating up and down. We know that it's going to land somewhere in between -1 and 1 or at those locations, but we can't specifically say what the answer is. So if we can't peg down an answer or our answer is infinite, we're going to say our integral diverges. So my suspicion is you would be just fine with these, calculating them. It's just that we need to talk about notation just a little bit. So let's pretend I don't see that that thing says infinity, and I just know that the antiderivative of natural log of x is of 1 over x is natural log of x. And then I need to evaluate from 1 to infinity. So plug in the infinity, plug in the 1, we get 0 here. Natural log of infinity, so let's talk about that. This is technically a limit, and me plugging this in is really improper math. But if I were trying to figure out what was going on at infinity with a natural log, well, it heads toward infinity. So since we get something infinite here, we get diverges. Okay, example 2, think of that as x to the -2. So when I take the antiderivative, I'm going to get add 1 to the exponent, divide by the new exponent. I'm going to just rewrite that really quick because it makes more sense to me to plug things into something that looks like that. If I plug in the infinity and then plug in the 1, I'm going to get, well, again, plugging in infinity is really technically bad math. We'll talk about that in a second. But basically I have something that's bottom heavy here, and then minus -1, so I get 1. So this one converges to 1. That's the way we would say that. Converges to 1. Okay, so again, while we might in fact calculate those fine, we're not supposed to plug in infinity. It's really not a number. It's really what's happening as something approaches infinity. So we should be writing limits. So here, same example, I have just written the correct notation. So we should say from 1 to b and make this a limit. That way when we're plugging something in, we're not saying natural log of infinity, we're saying natural log of b, but b is approaching infinity, which we know is infinite. Or here, some people actually like to say just does not exist there when we get an infinite limit, because we're supposed to technically get a number. Okay, so those are when we have infinite limits. We can also have problems where there's an asymptote at one of the limits. So in this case, it's 2, looking at example 3, I'm calling this one. So again, here's the correct notation, but let's just go ahead and calculate perhaps the way we would see it. And then what I would say is on a free response, we would want to make sure that we write the correct notation. So let's see, I'm going to think of this as the integral from 2 to 5. And let's think of this as x minus 2 to the -1/2. Okay, so let's add 1 to the exponent, so that becomes +1/2. Divide by the new exponent, but I don't really want to divide by 1/2. I'd rather put a 2 here, and then 5 to 2. So we can actually see that if we had not even known that this was an improper integral, it wouldn't make a difference at this point because plugging a 2 is no longer a problem. So we're going to get 2 and 3 to the 1/2, and then we're going to get -0. So that one converges to 2√3. Okay, sometimes the asymptote is in the middle, and sometimes that does make a difference. So we would want to split this integral from 2 to 3 where the asymptote is, and then from 3 to 5. And again, sometimes this does make a difference. So let's just see what's happening here. That integral would be natural log of x minus 3. I'm going to go ahead and kind of do bad math here for a second. So this is going to be natural log of 0 minus natural log of, well, it's -1, but it's absolute valued. So if I go back up to my sort of graph of natural log that I put up here, at 0, we're heading toward negative infinity. So that means this half diverges. So I'm just going to quit at this point, because if this half diverges, I can just say diverges. Now it might turn out that we get something like, well, this one's negative infinity and this one's positive infinity. But remember, adding those together doesn't always get us what we want. We might have to do a little bit more analysis to decide what's happening. So we're just going to leave that at diverges for the moment. What I would recommend at this point is that you stop the video and go do those problems, those improper integrals, and then come back and listen to the rest of this about comparison theorem. We're going to see the comparison theorem now and then later when we're talking about series. So if it doesn't totally sink in now, hopefully it will when we get to that unit. So sometimes we're asked if something converges or diverges, but we don't really know the integral or the antiderivative. So we're just going to compare it to something that we know about. So here it's kind of maybe difficult to explain, but let's just say f of x, which is this blue dashed line, let's say it diverges. And for some reason, we know that this red line, g of x, is greater than. Well, so if f of x diverges, let's just say it's infinite, and g of x is greater than something that's infinite, then g of x must also diverge. Well, let's say it's the opposite. Let's say that red line, that red curve, g of x converges, so it's finite. Let's pick a number. Let's say it's 7. So this is 7, and we're wondering about f of x. Well, since it's less than something that's 7, it must also converge. The problem with the comparison theorem is you know what you want, but you have to pick the comparison, and sometimes that can be difficult. So sometimes I like to show you, we'll see if I have, maybe do I have one that's a mistake? I think not in this one, but later when we get to unit 11, I'll show you what happens if we have something that's a mistake. So example 5 here, I have 1 plus e to the negative x over x, and part of what makes this one difficult to me is the e to the negative x. So let's just try to get rid of the e to the negative x and see what happens with 1 over x. So one of the first things I like to do is to graph it and see if that function that I picked is always greater than or always less than what we're talking about. So here the dotted red line is 1 over x, and it's kind of light, but that light blue line is the 1 plus e to the negative x over x. So it looks like the dotted line is always less, but can we say for sure? And I would say yes, because think about the numerator, e to the negative x is always at least a little bit positive. So our numerator of that one is always going to be a little bit bigger than 1. So we can safely say that. So let's remind ourselves what this one does. So again, bad notation, but I'm going to go ahead and do it this way anyhow. So we're going to get natural log of infinity minus natural log of 1. So something infinite, this one diverges. Okay, so let's just say, oh, this one is infinite. This guy is greater than something that's infinite. So now we know that this guy must also diverge. And then one more example here. Okay, so part of what makes this one difficult is the x squared. So if we just compare to e to the negative x, which is that green dotted line, we at least know that that green dotted line is above this one after some point. So e to the negative x is greater than or equal to e to the negative x squared, at least past, we'll say it probably is 1 if x is greater than or equal to 1. Okay, and that's okay because we know in between is a little bit finite. So let's figure out what's happening from 1 to infinity for e to the negative x, because that one we can do. So e to the stuff and then divided by the derivative of the stuff. Again, I am going to rewrite this so that I can hopefully make sense of it. So this is going to be -1 over e to the infinity minus 1 over e. So this is bottom heavy, which is 0. I forgot a negative in here. This is bottom heavy, so that's 0 minus -1 over e. So we got something finite. So that's our green one. This one is finite. Okay, this is less than something that's finite, so this must converge. So you'll see those toward the end of the lesson as you're working on your homework. So some statements are not helpful. So let's say we have something that's divergent and the thing that we have is less than that. So we're basically saying that our integral is less than infinity. Well, that's not helpful because, well, 12 is less than infinity, but so are some infinities. So we don't really know anything for that one. Or the reverse, if we have something that's convergent and we're looking at something that's greater than that, well, it's maybe greater than 7. Well, what's greater than 7? Well, 15, but also infinity. So that doesn't really help us. We have to be really careful about the comparison, which is why sometimes the comparison theorem can be a little bit more difficult. Again, we'll practice this now and we'll practice it again when we get to Unit 11. I think it's 11. We'll see.